Hello everyone. I'm just going to be waffling at you today about loci in the complex plane or loci in the Argand diagram. It's the next exercise in the book, and I tend to find that this is where people start to become a bit unstuck on the complex number stuff. It's not that bad actually once you get used to it, but it does feel a little bit weird at first, it has to be said. Let's start with a few facts, yeah? Firstly, let's talk about the modulus of Z. Yeah, when you're finding the modulus of Z, you're finding the distance that the complex number Z is away from the origin. So, if I was to write something like this, the complex number, well, the modulus of Z equals 2, what I'm saying is that if we let Z equal x plus iy, then I'm guaranteeing you that the square root of x squared plus y squared is 2. Yeah, that's what we're really saying here. Or indeed, let's take the square root over to the other side, that x squared plus y squared is 4. Now bear in mind here that x and y in your z equals x plus iy are just like coordinates in the complex plane. So if I was to write down size of z equals 2, or modulus of z equals 2, let's call it size of z equal 2, and I wanted to, and the question was sketch size of z equals 2 on the complex plane. I don't think they put it quite like that. Let's just have a quick look how they put it in the exercise. I think they say sketch the locus of z. Yeah, that's how they say. Sketch the locus of z if, and let me just rub that out there just so it looks a little bit easier to see what I'm going on about. If the size of z equals 2, yeah. If they if they ask you something like that, well, as you can see, this is just the circle, x squared plus y squared equals 2 squared. It's just a circle. This is the imaginary axis and this is the real axis. And so if I was asked to sketch that, I literally would just have a circle like this, and you can see as well, this would be 2i, that would be minus 2i. These are all the intercepts, by the way, minus 2 here, 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 and here. But every single complex number, like z, think of z as like a variable in that equation up there of size of z equals 2. Think of z as your variable, it's changing. But we're basically saying sketch the locus of all complex numbers whose length from the origin is 2. Well, naturally, all those complex numbers are going to be somewhere on that circle there. And that's why if they ever ask you to sketch size of z equals 2 or size of z equals k even, it's just going to represent a circle, center 0, 0, with a radius of k, not k squared, note, because modulus of z already square roots for you. So yeah, if you want to sketch that, it's just going to go through 2, 2i, minus 2i, and minus 2. And that's one of the easier ones, yeah? That's one of the ones where most people straight away say, okay, yeah, I get that. That seems pretty obvious. But, well, interestingly and quite fortunately, I think it gets a bit more interesting and it gets more difficult because how can we make sure now? So that's a general circle, center 0, 0. Yeah, let's just write that down. You might want to take that down in your notes. A circle, center 0, 0, radius k is always going to be given by that kind of equation. Yeah, always, always, always. So let's do one where the circle isn't in the center. How can we move that circle around the page? Well, here it gets a bit more interesting. Maybe I can write it down like this. Let me see how I think about how I'm going to explain this. Maybe by saying this. Okay, let me point out this. If you've ever got in the complex plane, if you've ever got like two complex numbers, let's call them Z1 and Z2, and these are going to be fixed, yeah? So let's just say we've got Z1, and Z1 can be 2 plus 3i, so it's 2 across 3 up, it's about here. And Z2, well, let's have that in the other quadrant, let's have that as 3 minus I, so that's 3 across I down, so that's about there, yeah? So here's Z1, and here's Z2. Let's actually write them on there, Z1 and Z2. Well, if I was to calculate the length of Z2 minus Z1, what have I really found there? Well, I found the distance between Z2 and Z1, because these numbers in the complex plane work exactly like vectors. I hope you can see that. It essentially is a vector, like best thought of as a vector in many ways. Because if I work out Z2 minus Z1, well, just like a vector, Z2 minus Z1 is this here, really. It's just not starting from the origin, but that would be like, if you like, Z2 minus Z1. Well, the length of Z2 minus Z1 is a distance from here to here. And you can see that it works like this, because what is Z2 minus Z1 in this example? Well, it's simply 2 minus 3, sorry, 3 minus 2, which is 1, and then minus 1 minus 3, which is minus 4i. Yeah? And the length of 1 minus 4i is simply going to be root 17, because it's 1 squared plus 4 squared square rooted. Well, that's exactly what this is. That's exactly what this is, because you've got, we've gone 2 across 3 up there, but we've gone 3 across 1 down. So going from Z1 to Z2, you're going to need to go 1 across and 4 down, and therefore to find the length of that line, you're doing 1 squared plus 4 squared square rooted. So generally speaking, if you've got two complex numbers and you take them away and you find the size of them, well, that will find you the length between those complex numbers. That should help us show how to move the circle around, because if I've got instead, let's do another sketch the locus question, because that's what all these questions are in the next exercise, and that's what I want you to get good at. It's a tricky skill, and there's lots of different types, and you want to go through it carefully and slowly. So let's sketch the locus. Sketch the locus of Z when, okay, Z minus, let's do, I'm going to put it in brackets straight away, actually. Z minus 2 plus I equals, I should have used a Pythagorean triple, actually. Can I use a Pythagorean triple? Just make it a bit clearer what's going on. Let's say 3 plus 4i equals 5. Yeah. So what kind of locus, what kind of path of points would this give us? Because remember, Z in all of these questions is not a fixed number. It is a variable, like X and Y on a normal curve. It is a variable. Consider it as Z equals X plus IY. Yeah. And I can even show you the algebraic kind of way of thinking about this in a second, just like I showed you the algebraic way last time, although it's nowhere near as quick as just knowing how these loci kind of work. Well, when we subtract two complex numbers, and Z is a complex number, and clearly 3 plus 4i is a complex number, when we subtract them, we're essentially finding, a way of getting from the end of one to the end of the other. Yeah. And if we're then finding the length of that, we're finding the distance between the 2 points. And we're saying the distance from Z, which varies, to our fixed point, which is 3 plus 4i, which is about, let's say here, we're saying, oh, let's draw it so I can fit it into my diagram. Yeah, so let's just say that's the point 3 plus 4, right? Yeah, because I'll write M here, you can see that's 4i, or I'll put 4i on it, it doesn't really matter. So that's an imaginary plane, that's a real plane. So the distance from our complex number, which is changing all the time, yeah, or it could be any complex number. We're looking for, if you like, all complex numbers which satisfy this, that the distance from our complex number to the point 3 plus 4i must always be equal to 5. Well, that's going to give us a circle. Centre 3 plus 4i, radius 5. Let me just pop a circle on there and talk a little bit more about this. Oh, I don't want it so squashed. Let me try again. Yeah, this is more or less working. Here we go. Okay, that's going to give us that kind of circle, because what is Z in this? And this is what I find students get confused about. Z is all these infinite points, all these different complex numbers on this circle, because, you know, call that Z, Z, Z. They're all different instances of Z. Yeah, Z1, Z2, Z3, all the way up to whatever, Z infinity. Basically, there is an infinite number of complex numbers for which, when you subtract 3 minus 4i, you get a distance of 5. One obvious complex number which satisfies that is a complex number 0 plus 0i. Yeah, 0 plus 0i, or in other words, the origin. Because if you do 0 minus 3 plus 4i, you obviously get minus 3 minus 4i. And the distance from there, you know, length of that point is, of course, yeah, it's going to be 5, basically. If you actually now find the length of minus 3 minus 4i, the length is 5. And so what are we saying here? We're saying, in this question, we've managed to find all points on that circle for whose the distance from the center of the circle, which is at 3 plus 4i, to our complex numbers which we're looking for, well, it's always going to be 5. Yeah, so that is how you move a circle around a page. This is just like function transformations as well. Think of it as a function transformation. What we're really doing here, whenever you do Z minus a complex number, you just move Z over, basically. That's what you're really doing. You're moving the circle over, if you like. So when we go from Z equals 5 to Z minus 3 plus 4i equals 5, we've actually just moved our circle 3 to the right and 4 up. I mean, look at it like this. If I expanded those brackets, I get Z minus 3 minus 4i. Well, what that actually does is move it 3 to the right, just like if you go from f of x to f of x minus 3. That moves it 3 to the right. Now, it's a bit more subtle with the y. The y always works like this, but it's more subtle seeing that it works like this. That's going to move it 4 up as well. If you do minus 4i, that's going to move it 4 up. It's just like function transformations. It truly is exactly like that. Okay, so that is how you move the circle around a page. And it's because, like I say, we're basically saying from a point, you know, if you remember that Z, when you've got Z, well, if you ever do Z2 minus Z1, it finds you the vector from Z2 to Z1. So these are all the vectors, if you like, coming off 3 plus 4i, but with a distance of 5. Okay, so that is how you sketch the locus of Z when you're dealing with a circle which doesn't have the center as its origin. Let's do some more loci in the plane. There's quite a few. There's a few to cover. The one I find really interesting, and it links back to this circle once again, is the perpendicular bisector one. So let's think about, what about if I had something not a million miles away from this, but we're going to have more moduli involved. Let's have sketch the locus of Z. Given that, let's do Z minus 1 plus I equals Z minus 3 minus 2i. Okay, that's what we're going to do. Now, if you've ever got this situation, Z minus a given complex number, and the length of that equals Z minus a different given complex number. So I want to make it very clear here what is fixed and what is my variable. My variable here is Z without a subscript. Yeah, this Z and this Z. My constants, my fixeds, my ones which are going to be given in the question are Z1 and Z2. We're basically saying sketch the path of points which Z lies on so that the distance from Z to one complex number is exactly the same as the distance from Z to another complex number. Now, if you've ever got that situation, well, that one is going to be represented by, let's just do our little complex number plane here, and I'm showing you the general case here. If, say, Z1 was here and Z2 was here, well, we need to make sure that the distance from Z to Z1 is exactly the same as the distance from Z to Z2. So let's draw a point on here. There, it kind of looks like the distance from Z to Z1 equals the distance from Z to Z2. Obviously, if I have Z right in between them, that's going to work as well. And down here, as long as I make an isosceles triangle, the distance from Z to Z1 there equals the distance from Z to Z2 there. That's because, do you recall, back in GCSE, the definition of a perpendicular bisector is the path of points such that any point on that path is the same. Let's say the perpendicular bisector of AB. Yeah. If I've got the perpendicular bisector of AB, the definition, if you like, is the path of points which are equidistant from A and from B. Yeah. So in other words, they're every point where the distance, every point P such that, and this could be P1, P2, P3, P4, every distance such that AP1 equals BP1, AP2 equals BP2, so on and so forth. The definition of a perpendicular bisector is the path of points which are equidistant from one given point and another given point. That's exactly what we're dealing with here. We're dealing with a perpendicular bisector. So if you know where Z1 is and then you know where Z2 is, you can actually come up with the perpendicular, the locus of Z will be this red line I'm going to draw here through all your other Zs. Yeah, it's just going to be the perpendicular bisector of those 2 points. But you must have it in brackets like this. So let's actually do this question now. If you want to sketch the locus of Z, given that Z minus 1 plus I in brackets equals Z minus 3 plus 2I not in brackets, well, the first thing you want to do, and this also applies to circles, is you want to rewrite this so that everything is given as Z minus a bracketed complex number. And that's going to become 3 plus 2I. Yeah. Oh. So make it a modulus. Okay, now we can do this straight away. We can just think, well, we know it's going to be a perpendicular bisector for those 2 complex numbers. We've got the 2 complex numbers, 1 plus I, and then we've got 3 plus 2I, and so I know if if they want just a quick sketch of them, I'm just going to sketch a perpendicular bisector. That's not very good, is it? I'm just going to sketch a perpendicular bisector, making it clear that, yeah, that goes through the middle. It's a perpendicular bisector, and that is your locus of Z. Yeah, it must go through those 2 points. Now, could you find the Cartesian equation of that? Yeah, well, yeah, you can. And you could do it algebraically, or you could do it just using like coordinate geometry. It's easier doing it using coordinate geometry and just thinking, well, if this was actually the coordinate 3, 2, and I know I shouldn't write it like that on a complex plane, but it will make this so much easier to work out. If you had 3, 2, and 1, 1, and you wanted to work out the equation of the perpendicular bisector, well, you firstly work out that as 2, 1.5. You'd also find that gradient here. The gradient is going to be, what is that? Change in y1 over change in x2. The gradient of that is half, which means this needs to have a gradient of -2. And now I can work out the Cartesian equation. Y minus 1.5 equals -2 times by x minus 2. Double everything. 2y minus 3 is -4x. That would have become +4, so +8. And so we've got 2y plus 4x equals 11. Okay, let me see if I can show you that another way. I'm going to do this like the more complicated way now. I'm going to do it algebraically. That's how I would have done it if I was given the choice. If they forced me to work out the Cartesian equation, and they never do this, by the way, but I just want to show you I get the same answer. I want to show myself in many ways that I get the same answer if I don't use this kind of diagrammatic geometric approach. If I was to do it algebraically, and this works by the way with the circles, it works with all of these, you can kind of do an algebraic approach instead, then what would I do? Well, I'd say, okay, let Z equal x plus iy, because then my x and y are exactly like x and y in the Cartesian plane. They work the same way. Then what am I going to have? X plus iy minus 1 minus I. equals x plus iy minus 3 minus 2i. Okay, let's simplify that by collecting the real terms, x minus 1, and collecting the imaginary terms, plus y times, also plus I times. I want all the I terms together here. I times y, and then minus 1, isn't it? Yeah, perfect. I'm going to do the same over here. X minus 3, that's the real part. And then plus I times by y minus 2. That's the imaginary part. Now, if you've ever got the length of one complex number equals the length of another complex number, then what you can say is the square root of, you always find the modulus of a complex number in the same way, that squared plus this one squared. Yeah, it's going to be the same over here, square root of x minus 3 squared plus y minus 2 squared. We'll quickly work that out. Like I said, I'd never do it like this, but I just want to show you get the same answer. Ignore the square root, square both sides if you like. You're going to get x squared minus 2x plus 1 plus y squared minus 2y plus 1 equals x squared minus 6x plus 9 plus y squared minus 4y plus 4. Loads of things are going to cancel here. There's an x squared on both sides. There's a y squared on both sides. We're then going to have 4x over here when we add the 6x. We're going to have 4y plus negative 2y is 2y. I think I left all the numbers on the right hand side, didn't I? And then I've got 9 plus 4 is 13, take away 2, 11. Yeah, and so I get exactly the same. I think that's exactly the same as what I just got, isn't it? I can't remember now. Hopefully I've got exactly the same answer as what I got before. I believe it is. I remember there was 11 involved. Tell me and laugh at me if I've now got a subsequent different answer, but I think it's the same. Okay, so that is a perpendicular bisector. Hold on to your hats, we've still got more to go. Okay, so what else have we got? I'm forgetting myself now what what ones. We've got the argument ones, haven't we? We've got the ones with the argument, the half lines. There were more difficult ones actually under the old syllabus, but they seem to have gone, some of the really nasty ones, which is nice. It's not all got worse. Okay, let's do arg of Z equals pi over 4. Let's do that one first. Then we're going to do arg of Z minus I equals pi over 6. Okay, the first one. All we're saying here is our complex number must have an argument of pi over 4. Now recall, what is the argument? It is the angle from the x-axis, better draw this really, the angle from the x-axis up to the point where the complex number is. Yeah, so if I just give you an example complex number, let's say 1 plus 2i, yeah, the argument of 1 plus 2i geometrically is just that angle there, yeah. That is what the argument is. It's the angle between the complex number. If you draw a line, and that's why we often draw thick lines from the origin to represent our complex numbers, more often than not, is so we can clearly see what we're talking about here. It's always in relation to the origin. And so it is basically the angle the complex number makes with the origin. Well, if I want to sketch a locus, because I'm not sure what complex number Z actually is, this is what I'd have to do. Very similar, very similar. What we're going to do, we're just going to make sure all our complex numbers have to be at 45 degrees. Pi over 4 is 45 degrees. They always work in radians on a complex plane. I almost never see them working in degrees, so get used to radians here. Okay, we want every complex number so that the angle that the complex number would make, if you drew a line out from the origin, the angle's got to be 45 degrees. Well, that will give you a half line. It's called a half line, and I'm just going to delete that out there, and I'll tell you why in a second. It's basically going to be every complex number on that line going on up there, and they normally put an arrow on the end of it to show you. Now, one of the things they are keen to sort of point out in the book is that you have to exclude the origin here, because the origin is not pi over at an angle of pi over 4 away from away from the origin. You exclude the point itself, the origin itself, but every other number on that line, if you were to draw a line from the origin to that Z, all these Zs, these are different possible Zs here, here, going on forever in that direction. It gives you a half line. These are called half lines, yeah? And that would be the locus such that argz equals pi over 4, because that angle is pi over 4. Okay, if you're happy with that, then we can do the next one. Now, arg of z minus I, well, recall that whenever you swap z with, z minus z1, that just moves you from the origin up to z1. Think back to the circle. It just moved you from the origin up to z1. That's exactly the way it's going to work here as well. So what do we got? We've got, let's draw the complex plane. Now we're dealing with z minus I here, which moves us immediately up to I on the complex plane. And then we want, now it's pi over 6, that's about 30 degrees, so it's going to be something like that. We just want all points on that line now. It helps sometimes to dot the line down here. It means it's the angle it makes. It's like a bearing. It's a direction it makes. That is pi over 6. The half line starts from whichever complex number it is here, which you're taking away, and then you're just going to be left with an angle of pi over 6 there. Sometimes people want, like almost, sometimes it helps people to have a visual proof that this actually works. So if you actually were to were able to identify another complex number on this line, let's see if we can find another complex number on this line, because that's 30 degrees. What's sine 30? Sine 30 is a half. So if we had sine pi over 6 1/2, that's going to be opposite divided by half. Let's think of tan actually. Tan of pi over 6, tan of 30 is 1 over root 3. So if we had that as 1, the opposite as 1, and the adjacent as root 3, then what I could say is that would give me a complex number here. Sorry, I'm just waffling to myself here. I just want to show you, if you were to draw that out carefully, I believe that the point root 3 plus 2i would be on this line. Yeah? Now let's see if it satisfies this statement. The argument of root 3 plus 2i minus I, well, that equals the argument of root 3 plus I. Now, what is the argument of the complex number root 3 plus I? Well, that's root 3 in the x direction, I in the right direction. So it's just like this, root 3 I. Sure enough, it's going to be tan theta there is 1 over root 3, and sure enough you get pi over 6. So I'm just trying to demonstrate that this actually works, this way of thinking about it. It genuinely works. There we go, and that is how you sketch the locus of an argument. Now I just want to show you like what I would regard as a tough question. If you had something like this, there's all sorts of tough questions actually here, but I want to show you one which is similar to a very common kind of question, because they can be tough here. Please do let me know if you get stuck on this, like preferably in the Zoom meeting tomorrow. That would be handy. But I don't mind going over some of this again then, because I totally understand. It's a tricky idea, this. Okay, so example toughies, if I can call you this an example tough question. Excuse me. Okay, that will do. Okay, example. Right. Firstly, let's sketch the locus of Z, given that Z minus 5 minus 3i, I'm pinching this from the exercise, equals, or the examples, equals 3. Yeah? If you wanted to sketch that, first things first, turn it into Z minus a complex number in brackets. Well, that will give you 5 plus 3i equals 3. Now we can sketch it, no problem at all. And this is just part A, this is the easier bit. Oh, let's do this properly. So it doesn't have to be particularly neat, but it does have to be in proportion. We're going 5 across, 3 up. 3i if you like here, but we know it's imaginary. Real. Okay, so that's the center of our circle, but it's radius 3. So we want to make sure that it's touching the x-axis because it's got radius 3. Yeah, its center is at 5, 3. Now, an interesting way to finish off this question is when they say something like, hence find, oh, hence, or just find the maximum value. I'll say the maximum and minimum values of Argz. Yeah. Now, this is a good question. I like this kind of question. I really do. Because remember, Z is just floating around on the edge of this circle. Yeah. And to find the argument of Z, you're going to have to draw a line up to it and find the angle that makes with the x-axis. So let's actually do that. Let's think about that. Z is somewhere on that circle. Let's do it in blue. Z is somewhere on this circle. It could be anywhere on this circle. Whereabouts is it going to be to find you the minimum value of Z? And whereabouts is it going to be to find you the maximum value of, sorry, Argz? Well, if Z is all the way up to there where we got a tangent to it, or if Z is as small as down there, those are going to give you the extremes for the argument. Yeah. I might do a different question after this, actually, a similar one. That will find you the maximum angle that Z can be at in relation to the origin and the minimum value that Z can be at in relation to that origin. Now, how are we going to do that? Well, we could draw two little right-angled triangles here, couldn't we? Make a little kite. It's quite windy outside. Why not make a kite? Okay, so now we've got this. We can actually find the argument. Yeah. Now, clearly the minimum value is just going to be 0 because it corresponds to when you have the complex number Z equals 5, which sounds very much like a real number. And yeah, that will certainly have the minimum argz because the value of argz for Z equals 5 is simply 0. Yeah. So the minimum argz is 0. The maximum is going to be whatever this value is doubled. Yeah. And you can see there that tan theta is going to be 3/5. That can help you find theta. And therefore we get where's my calculator? Here it is. So making sure I'm in radians. Inverse tan of 3/5. That gives me 0.54, but I want to double that for the maximum value because I've got two thetas in there. They're identical congruent triangles. They've both got 5 across 3. Well, that's a radius of 3. That's a distance of 5. That's 3. That's 5, that's 3, that's 5. So they're exactly the same triangle. So we just got to double that now times 2. And so the max of argz is going to be 1.08 radians. And that is a tough question. Let's do one more related to this. If I can just take off everything I've just done for the argument, I'm now going to rephrase the question and do a part C. So let me just take all this back. Okay, let's change the question now to and I'll call it C. C. Find the maximum value or find the minimum and maximum value of the modulus of Z this time. Now remember, what is the modulus of Z? And Z is just something floating around on this triangle. Let's do it in a different color to before. Let's do it as red. So Z's somewhere around on this circle, lurking there. And we want to maximize out or minimize its distance from the origin. Well, that means that we need to think about, if you like, a little line going through the origin and through the center of the circle like that. Yeah, the minimum Z is going to occur here, and the maximum Z is going to occur there. Now, what's the best way of doing this? I favor kind of just using like a Cartesian approach, really, I guess. There's lots of ways of thinking about it. We just need to identify the minimum and maximum value of Z. Well, I suppose let's actually do it like this. The distance from the center to there, the distance from the center, distance from origin to center, is just root 34. Because it's 5 squared plus 3 squared square rooted. And so, if we call this one Z1 and we call that one Z2, yeah, for the length of Z1, that's just going to be root 34 take away 3 because the radius of the circle was 3. Whereas for Z2, yeah, that's the minimum value of Z. But for Z2, we could just do root 34 plus 3. And that's the maximum value of Z. And that's another example of like a tough little question at the end on these, but you get used to them. You really do get used to them. Okay, I hope that was useful. I think this has worked out to be a longer video than I was perhaps hoping for it to be. But yeah, do ask me in the Zoom lesson tomorrow or another time if you're stuck on any of these problems. They're good practice, and we'll be working on them at least for today and tomorrow's lesson and probably a little bit next week. Okay, thanks for listening. Bye-bye.